So what kind of ODEs did we talk about last time? Or what's an ODE? Let's start for there. It's even lower level.
Equation with a derivative.
Partial equation with a derivative, an equation with a derivative, and it's just one kind of derivative. Derivative with respect to one variable because it's ordinary. And we categorize them into linear and nonlinear. We talked about how linear was going to be easier to solve. We categorized them into homogeneous and inhomogeneous. And we talked about how the homogeneous solution was an easier one to guess, and it comes with sort of free parameters that can be adjusted with what kind of conditions? Boundary or initial conditions. And then we talked a little bit about the particular solution, which is like the special part that cancels the inhomogeneous part. So we're going to do a couple of geophysical examples today, 3 or 4, that are kind of classic first order differential equations. So, and they'll all be linear, and we'll start to see how the solution goes for these kind of problems, and some of them are kind of fun. So we will, and all of these are coming from the notes, so they're all there in a much more expansive version, but I think it'll be useful for us to discuss them in the context of what we learned on Monday. And then on Friday, we're going to do some second order differential equations. So we'll see how those happen. And then next week, we'll switch over to this other way of thinking about things for a bit. Okay. So, what's the hydrostatic balance? You guys learned this in other classes? What's the conceptual idea of the hydrostatic balance?
It's like when fluid's not moving, there's like pressure.
Yeah. So this pressure that accumulates just from, and the way that I think of it is it's like you're interested in, so there's a vertical coordinate and there's something like fluid or the atmosphere, or even it could be solid earth sitting on top of you. And so the pressure is increasing with depth. So the pressure is low up here and the pressure is high down here. And it turns out that it increases based on the weight of what's on top of you. So that this, if this was moving fast, the pressure would actually respond somewhat to the motion. So it's called hydrostatic, which is, the water is stationary. So it means when it's not moving, the only force that's really going on is the force of gravity. And what you might describe in the middle is some kind of density. So the density might also be a function of z. We're going to talk about different ways to think about that. Does that make sense? So if the pressure accumulates based on the weight of what's on top of you, how can we write a differential equation that has something to do with that? How does it mean? What do I mean by saying the pressure accumulates? The rate of pressure change with what? Yeah. So the pressure dz is something, and the something is going to depend on gravity. And what else is it going to depend on? Density. So density times gravity, or you could think of density as mass per unit volume. And so this is like this is the weight per unit volume. The mass times the gravity per unit volume is what's increasing the pressure. Or the weight per unit area is what's accumulating the pressure as you go down and see. Does that make sense, everybody? Okay, so what sign should be here?
A negative.
A negative. Why is it negative?
It increases when z
Yeah, so the pressure is going down as Z goes up for positive density. And negative density doesn't make much sense. So we don't have to worry about that case. Okay, so this is the hydrostatic balance. It's actually the vertical momentum equation for a fluid or a solid in the case where the stresses, internal stresses are negligible. And so the only thing you have is the gravitational force, and it's balancing the pressure gradient force. Okay, so when we get to continuum mechanics, we'll see how this comes from that. But this is a nicer way of thinking about it, just force balances. Okay, so how to solve that equation? Let's think about a few different examples. Well, how would you go about solving it? What did we learn last time? About the short method.
GZ over and integrate.
Yeah, so let's make it this explicit. This is a function of Z. So I can put all the Z's on this side and all the P's on this side and write down something that we can integrate. I can put the G out front because well, actually I keep the G inside. Let's keep the G inside. If I was getting really fancy and I was thinking about something like the a deep atmosphere, really, really tall, G might actually decrease with altitude as we got far enough away from the center of the Earth. So we can keep it inside here. What about the limits on my integrals? I could use none, in which case I would have pressure equals minus this integral plus some constant. That would be one way I could do it. Or I could choose a convenient location, a convenient altitude or elevation where I knew what the pressure was. So I could bring this over and say that this was pressure minus the pressure at some 0. Let's just say we know where 0 is, and this is P of 0. And that might be the surface of the ocean, that might be the top of the atmosphere, that might be the surface of the land, whatever. I measure the pressure there, and everywhere else I'm trying to figure out what it is. Okay? And then this one we integrated from 0 to whatever Z I was calculating on, e.g. Z. Everybody see how that works? Okay. So what are some profiles of rho that I might be interested in? How does rho vary in a liquid, incompressible liquid? It's constant, right? So water is a little bit compressible, but to a good approximation, I could say that it's got the same density, which is about 1 gram per cubic centimeter. And if this is constant, and we take Z as constant, I can just solve that equation. P minus E naught equals rho naught G Z minus 0. Or P equals P naught minus rho naught GZ. So what does that look like? How does that pressure increase? Let's make a graph. Pressure. Sorry, I put Z in the upwards direction because otherwise I get confused if I put it sideways. Even though this is the independent variable, this is the dependent. Like putting it vertical makes me think that it's the vertical direction. So what does that look like? If I have 0 here, or in the ocean case, let's actually put 0 up top. But let's do it like this. We'll put 0 in the middle. So 0 is the surface of the ocean. So that's like 1 bar, 1 atmosphere of pressure. And what does it do below? Atmosphere. Oh, 1 atmosphere. So how does the pressure go? It increases like a straight line, right? So this is a linear differential equation whose solution is actually a straight line. So it's going to increase linearly, and the slope is going to be rho naught G minus rho naught G is the pressure dc. Everybody on board with that? What about the atmosphere? We're talking about the ocean. Now let's look up into the atmosphere. Do we expect the pressure to be constant? Or do we expect the density to be constant in the atmosphere? It's not, right? At the top of the atmosphere, the density is really, really low. And at the bottom, it's really, really high. So it's probably gonna match one atmosphere at the interface, but now what does it do above? So what's a physical law that relates the pressure to the density for a gas? It also involves the temperature. The ideal gas. So if we, instead of taking our ocean case, we take the atmospheric case, now we still have that formula, P minus P naught equals the integral of rho G dz from 0 to z with a minus sign. But now rho is going to be something else. Rho is going to be the rho that comes out of the atmospheric gas law, which is convenient to write it this way. So density is, so this is pressure times volume equals number of molecules times temperature, but then move the volume over, divide it, the number of molecules, change the constant R to be this one that's based on that has the right units for this one. And then, so basically the pressure is proportional to the temperature and the pressure is proportional to the density. You increase the density, you increase the pressure, increase the temperature, increase the pressure. That's the idea of gas law. So, how does the temperature increase in the atmosphere? This is kind of fun.
Not linearly, like it decreases, but then it hits the thermosphere and increases and then decreases.
Exactly, so it's a rather complicated thing that it has kind of wiggles depending on radiation and stuff. Let's make our law simple and just pick a constant. So this is an isothermal atmosphere, which is an approximation that would be like if you let the diffusion of heat in the atmosphere equilibrate, it would just all have the same temperature. So that's fine as a kind of base case. This is the absolute temperature, so it's actually not quite as bad of a problem as you might think, because it's like 273, between like 240 and 300 is actually not a bad range, so it's only kind of a 10% variation rather than a huge variation, because it's in Kelvin rather than in Celsius, but whatever. So let's take that for simplicity. So now, look back over here, we have this differential equation, but now rho is a function of z because rho is a function of pressure. So what does our differential equation look like? dP dz equals minus rho, but rho is what? G. Oops. G. So what kind of an equation is that? Ordinary, oops, sorry. Should have used curly brackets. It's an ordinary differential equation. It's an ordinary differential equation in Z. The other one had a constant. So this was this one with this being 0, what kind of differential equation was that? That was an ordinary differential equation, an inhomogeneous ordinary differential equation, right? Because we had a term that didn't depend on the variable, that didn't depend on pressure. But now when we get in the atmosphere, we have what kind of a differential equation?
Homogeneous.
Homogeneous, because if I set the pressure to 0, both of these terms would go away. If I set the pressure to 0, this one, with the constant rho naught, this term would not go away. Okay, so it's fundamentally different between the compressible ocean and the ideal gas atmosphere. Okay, so how do we solve this equation? This is a homogeneous, first order, constant coefficient, linear differential equation. Talked about this one last time.
It's gotta be an exponential form.
Got to be an exponential. So we gas, the pressure equals A times E to the Z over, wait, I'm using gamma because, all right, I'll stick with gamma. This thing is called the scale height. So this is actually something that has a symbol that normally goes with it. But okay, now how do we find A and how do we find gamma? This is my equation. How do I get these things? If I plug this into there, what do I get? What's the PdZ?
A over gamma.
A over gamma, E, Z over gamma. That's the left-hand side, which equals what? P over R S T naught G. Well, what's P? That's also A, E to the Z over gamma, right? So I can cancel out the A, E to the Z over gamma on both sides and solve. The A gets canceled too. And solve that gamma equals, flip it upside down, RS T naught over G, and there's a minus sign because I didn't put it in the other one. Let's actually make our lives a little easier and put a minus sign here. Because there's a minus sign here. So the scale height, so that tells us what this gamma factor is. It's something that depends on the ideal gas constant, gravity, and temperature. But what does the pressure do? Starts off, what value is it at Z equals 0 at the surface? It's A. And hey, if we want to match it on this one, we could just say that's equals 1 atmosphere. So we could take this A to be, let's just keep A. The A equals 1 atmosphere. Convenient, it was already called A. It's 1 atmosphere. Then what does it do as we go up? From Z goes greater than 0. Zero. It decreases exponentially, asymptoting to 0 pressure at infinite height. So in the atmosphere, the pressure increase is exponential. In the ocean, it's linear. And it's the same differential equation in both cases. It just has to do with whether you're compressible or not. Everybody, that makes sense to everybody? So the last example, which we're not going to solve, but which I drew a picture of, is like, oh man. Is, so, if this is the mantle down here, and this is the mountain, and this is the ocean, and this is the continental crust. So I'm trying to draw crustal thicknesses. So if the crust has one density, the mantle has another density, and the ocean has another density, and the atmosphere has another density, how do I think about, can I use that problem? Can I do this same problem? So figure out the steady state, the hydrostatic pressure field for all this? Still assuming that the stresses are not important? Yeah, so how do I do it?
Is it just isosceles?
Yeah, but isn't that the same? How do I get it from there? So what am I gonna think about? What do I need to know? So we did the atmospheric problems. The atmosphere is gonna be the same game pretty much everywhere we go. It's gonna be the little exponential of the case. But now what do I do? When I get to the surface of the ocean, now I'm gonna go linear for a while. Then what happens when I hit the crust? Or the seafloor? Linear but steeper because the density is higher. And then when we get to the mantle, it's higher still. So if it was an okay approximation, which is not great, but it's okay, to say there was a mantle density that was constant and a crustal density that was constant, then I could do that whole game.
Isn't that shallower?
We'll make it shallow? No, sorry, pressure's going this way. Pressure. Easy. Sorry, make higher pressure faster. So, yes, it is. Yes, this is shallower slope, but I've flipped the axis, so it's a steeper slope in the right direction. What about this thing? I've drawn the crust is going down underneath the mountain. Can we explain why that is?
Isostatic equilibrium.
It is, that's the word for it. Can we know it from this hydrostatic balance? Can we actually kind of estimate it? I claim we can. And this is sort of a homework problem. If I want the pressure to be the same at these 2 points, and to be the same at the atmospheric end, this one has to be taller than this one to make density add up to the same amount by the time we get here. So if I lift up at the top, I have to push down with the less dense material in order to have the density, the pressure arrive at the same value at the same time. Which isn't so obvious, but it's like basically intersecting slopes. You want the slopes to intersect down here at the right point, so you have to figure out how thick the different layers have to be for that to work. And the same is true here, which I replaced the ocean density with crustal density, and I actually show that you can show that it has to be thicker here rather than there, and it has to start higher up. Okay? So these are fun games to play. But it's all just this one little differential equation. So that's our first differential equation, and you can see how this innocuous looking thing actually does a whole lot more than an algebraic equation of the equivalent number of symbols. Okay? And this is not a line. These are piecewise linear and exponential. The exponential is definitely not a line. The ocean case is a line. So this is a linear equation, but its solutions are not straight lines, which we keep saying, but I'm going to say it one more time because we're still paying attention. Because what we mean by linear equation is not the equation whose solution is a line. It means something that when you add 2 solutions together, that is also a solution. Okay? All right, so that was one good example. Sorry. Any other questions about that before we go on to the next one? I did one thing kind of fast. So I had the arbitrary constant here, and the other one, how did I set them? I set a boundary condition, and I chose the boundary condition between the atmosphere and the ocean because I knew that that was close to 1 atmosphere. But in either one of those problems, it didn't really matter. I could have set the boundary condition in the atmosphere at infinite height to be 0, but that wouldn't have worked. I mean, set it at some height. We could have set it at some other value. But if they all came through in the boundary conditions, which in that problem was like totally obvious what the boundary condition should be. The pressure should just match from fluid to fluid as we went along. And this one, the whole game is making these not have kinks, right? So that was that. In the hydrostatic problem, it was really natural. It's a little less natural in the second order differential equations that we're going to talk about next time. All right, so that was one example. Example number 2. For those of you who've been in my oceanography class, this is a familiar one, but we're going to do a different problem than we did there. So imagine we have an estuary. It's like, so there's a river, and there's evaporation, and there's precipitation, and then there's an exchange flow where fresher water is going out with one salinity going out, and saltier water is coming in, it's in, and so this is like Narragansett Bay. So we're up here at a river, Providence River, coming in on this side, and then over down by Newport, there's an exchange flow where salty water is going in and fresher water is coming out. And in our region, the amount of incoming fresh water, so precipitation plus runoff, is greater than the evaporation. So which one of these is going to be greater? Just think about that. The outflow or the inflow? The outflow, because I'm putting in extra water across the bay, so it's got to come out. And then the salinity going out is also going to be fresher than the salinity coming in. And so there's a nice budget that you can make for this, which I do in the notes for like, how do we think about all these pieces? But the budget is actually sort of steady state. It assumes like, make all these things balanced, make the amount of salt coming and going balanced, make the amount of fresh water coming and going balanced, gives you some equations. But I want to think about a different problem, which is what if we put some pollution in the river? We're up here making boron silver, and we're polluting the river. And then we see where it's going. What do you think happens? It eventually flows out. Will there be some persistent concentration here? There will be. So there won't be any, so in the simplest case, there won't be any pollution coming in, but there'll be some going out, and it'll be a different concentration than this one because it'll dilute a little bit before it goes out. So the concentration of pollution is going out, there'll be one over here, there'll be one over here, and there'll be one concentration in the middle. So I don't want to solve that one. That one is solved in the notes for the steady state, but there would be a steady state pollution eventually, after you let it run for a while, it will eventually come to a steady state. What I want to talk about is this differential equation. Which comes out, volume, P out, minus P out in a steady state. Okay, so if you go through all the budgets and think about them, and then you think about changing the amount of pollution that's coming into the river, we could think about turning off the pollution source. What would then happen eventually? It would eventually flush out. But how does the pollution concentration evolve while we're waiting for that change to occur? Does that make sense to everybody? This is the equation that comes out if you solve for that, and we can approximate it and make it something that looks really good, which is V out over V. This one is just, if we say this is a source, this one is a in. This is there's the steady state solution, and then there's the present solution, the pollution concentration in the bay right now. Those are a little different. And so I claim that if you go through this, you'll find that the present concentration of pollution in the bay minus the steady state, DDT of that will go like the flow rate out divided by the volume of the bay with that same thing over here. So I go through all the budgets and kind of rationale to get to that, and the notes. What kind of a differential equation is this? What's my variable I'm solving for? P, or maybe the anomaly of P from the steady state, which is in terms of the anomaly of the P from the steady state, it's on both sides of the equations. So that's really convenient because what kind of an equation is that? That makes it homogeneous. The steady state, there isn't any d by dt of the steady state, is there? So I can actually set this one to 0, but then I have a P steady state over here and a P. So that would be an inhomogeneous solution. But this is a really simple problem in that adding P steady state onto whatever I call P makes it homogeneous. So this is the particular solution. It's just adding P steady state on this side of the equation. So P, thing of P is the anomaly from the steady state, takes our inhomogeneous equation and makes it into a homogeneous equation, very simply. Does that make sense to everybody? So the particular solution is not a crazy thing. The particular solution can be something that's really sensible, which is, in this case, as soon as I switch into the anomaly framing, the particular solution is what I would guess. It's sort of, yeah, a particular solution to this equation is the steady state one, which is neglect the d by dt term and set the pollution level to the steady state pollution level. That's a particular solution. Okay? How do I solve this equation? First order linear, homogeneous, constant coefficient, differential equation. Is it any different than the atmosphere problem we just did? I mean, the symbols are all different, but it's still ddt, d by d something of a variable equals a constant coefficient times that same thing. So that we know what the answer is. P equals P steady state plus some initial value, E the minus V out over volume times time. So I jumped a couple of steps there. This is the general solution. And I'm just calling the coefficient P, the initial value, but so just put a 0 on it. Here's the particular solution. There's the solution. There's the solution for all of them. And this one is just a parameter that I'm given. What's the initial value of pollution in the bay? That makes sense? The time t was, or this is, let me write it a better way. I'll write it in a better way. P0 minus PSS times that. Why? So why is that more convenient? Because P0, if at time T0, is actually the initial pollution concentration. Because the PSSs will cancel out. And I was free to write anything, any coefficient I wanted, so this is a convenient way. So if P0 is 0, no pollution in the bay, what does it look like? PSS times 1 minus e to the minus p out over v times time. So what does that formula look like? If I plot it in time, amount of pollution, P steady state, starts at 0 and it goes where? Up and toward the final value exponentially. Or I could flip this around and say, suppose we turn off the source of pollution, and so P steady state is 0, and I start with some pollution in the bay at the beginning. So now the P steady, this becomes P0, and P steady state is down here at 0. and it would go exponentially down. And this time scale for decay is set by how much flow out of the bay there is and how much volume of the bay there is. So if the flow rate was faster, if there was more exchange with the ocean, it would flush out faster. If the bay was bigger, it would take longer to flush out. Does that make sense? So this is totally different problem, same differential equation. And this one is really nice because it shows how the particular solution pops into existence in kind of a nice way. Okay? All right, that's number 3. Now here's the fun one. We're going to consider a nonlinear first order differential equation. Okay, so this is an energy balance for the Earth. So here's the Earth. And there's energy coming in from the sun, and radiation going out, and radiation coming in. So by radiation, I just mean, electromagnetic radiation, light. So this is coming in from the sun, and then some part of it, so let's say shortwave, so people know what that means. So it's visible light, right, mostly. And so what happens when the sunlight hits the Earth?
30% is reflected and 70%.
Some of it's reflected, which depends a lot on how big the ice sheets are and how cloudy it is. So if it's, there's an albedo effect that has to do with ice sheets, and there's also a part that has to do with how cloudy it is. And what about this part? What's that depend on? Greenhouse gases, yeah. And okay, what's the other part? It does depend on greenhouse gases, but it also depends on one other really important parameter. Temperature of the Earth. So this is a function of the greenhouse gas concentration and then temperature. This is, I'm definitely going to write this amount. So the amount that's net of this is 1 minus the albedo. And if I think of the albedo as being ice sheet driven, the albedo is probably a function of temperature. Does that make sense? So if I colder temperatures, I have more ice. Okay, so this little toy model, I found one called by Geophysical and GEOL, which is very hard to say. But this is based on the Geophysical model, also hard to say, from the 60s. So how much absorbed solar radiation, how is the absorbed solar radiation going to vary as a function of temperature? So I mean, the Rn part of this minus the part that's bouncing out. What kind of a function do you think that would look like? What would it look like if we melt all the ice? What is it going to look like? It'll increase up until all the ice is gone, and then it'll be constant. So it'll be something like straight line going down like this. And this is when we've got as much ice as we're going to get. This is when we've got no ice. And in between, we've got some kind of sloping function. Okay. And what about this guy? How do you think that's going to vary? Anybody know the Stefan Boltzmann law? It goes like sigma T to the 4th, and then there's a greenhouse gas part, which you could also take as a function of temperature because water vapor is part of it. But how does sigma T to the 4th look on that kind of a figure? I was gonna make the amount of, so this is our in curve. What's our R out curve look like? And sigma t to the fourth gets bigger as the temperature gets hotter. Yeah, and it just kind of curves, right? So we can imagine sigma t to the fourth looking something like this. Or we could imagine it to look something like this. Maybe the greenhouse gases are different, or maybe something like this. Maybe something like this. So let's interpret this rightmost one. When is R out going to equal Rn? Sorry, does everybody follow what I'm saying? These are, if I change maybe the greenhouse gases, I'm jumping around between different versions of this. I could also change aspects of the ice sheets and move the other one around. But I just want to make one point. So this is R out, and this is Rn. So when would the radiation be in balance? Yeah, that was what you were going to say too. Okay. So here we have an intersection. Cool. So if we start our model Earth off right here, what's going to happen to the temperature? It's just going to stay the same. What about if we started off down here? Then at this temperature, R out and Rn, how do they relate? It's more Rn, so then what happens to the plant? Temperature goes up, we move along this curve back to that point. This way. What if I started up here? Now, R out is greater than Rn. What happens to the temperature? It's going to go down. And we're going to come back to this point. So this point is a steady state solution, and it's a stable one. If we perturb away from it, we just come right back to it. That make sense to everybody? Okay, what if we change our R out parameters and now we're living on this curve? This one is going to be the same as that one, just a slightly different value of temperature. What about this one? This one's stable. So if I perturb and go over here, or go over here, what happens? Go over here, which one's bigger, R out or Rn? Rn. So then we do what? When warm, we go back to there. What about here? Down. So this one is stable too. What about this one? Different. What if I'm over here? Which is bigger, R out or Rn? Rn is bigger. So we go to that one. For here, we go to that one. This is an unstable steady state solution. So if we were sitting right on that temperature, the system would be stable. But if we kicked it a little bit, we would go to one of the other steady states. This is the kind of explanation that we're going to talk about when we talk about dynamical systems. This is the sort of thinking that we're going to be thinking about. So we didn't solve this we haven't even written down the differential equation yet. But we started to think about how it behaves by just thinking about the physics of the situation. What about this one, where it just kisses that point? What kind of a system is that? It's stable on this side and unstable on that side. Or no, stable on that side and unstable on this side. So it's half stable. So we draw it like maybe a half circle. If I'm on that side, I come back. But if I'm on this side, I just zoom away. Does that make sense, everybody? Okay, last thing before we solve this simple, or before we write down what the simple differential equation is. What if I'm changing this in time? What if I'm altering my greenhouse gas concentration and moving my R outs around? Suppose we live on this bottom branch, and then we push ourselves that way. What happens? There'll be one point where it just kisses this one, and then what happens next? What happens when that solution intersection disappears?
There's a new temperature.
We're gonna have to go all the way up to this one. There's not any other solution. So we might have been happily sitting down here on our partially ice-covered planet, and if our greenhouse gases got enough, there would be a collapse, and we would lose all the ice sheets and go up here. Okay? So that's what this simple model is supposed to explain, and it's all in there. All right. So I'm going to write out the full equations, and then we're going to do one quick step, and then we're going to talk about something which is enough to do the homework. Oh, so we weren't too explicit, but well, I'll do it a second. Hold on. So R in of temperature, R minus R out of temperature. So the temperature is the difference, R in minus R out, with some heat capacity. So that's the fundamental differential equation. And then there are these extremely elaborate equations . This is all written down in notes, so you don't really have to write it down. 1 minus tanh kappa T minus TC. That's it. R out equals sigma, approximately equal to sigma T to the fourth 1 minus M times tanh 6th power T naught to the 6th power. Okay. All right. Here's the incoming radiation. Depends on the albedo. And if we want to make something that's shaped kind of like that, you can do it with a hyperbolic tangent with some extra parameters. Here's the outgoing radiation. So there's the Stefan-Boltzmann part, sigma T to the fourth. And then there's a greenhouse gas effect, which has a coefficient. Then it has some big power of temperature over here. Why does the amount of greenhouse gases depend on the temperature? Which greenhouse gas responds to changes in temperature?
If temperature increases, then like weathering increases, and so CO2 is drawn down.
That's true on a long time scale. On an even shorter time scale, the amount of water vapor in the atmosphere goes up if you increase the temperature. So what they had in mind here was that you increase the humidity of the air and then trap more radiation. But you're right, other geophysical effects might also have a temperature-dependent amount of concentration. Okay, so these are the equations they do. Are these linear? Are these linear and nonlinear differential equations? So what's the variable we're solving for? Temperature. That's our unknown. And in this form, it looks nice and linear, except when you look, temperature in here is hiding inside of a hyperbolic tangent. And temperature in here is hiding inside of a hyperbolic tangent of temperature to the 6th power, temperature to the 4th power. Those are definitely not linear. Okay, so we're stumped, but what could we do? How do I take a nonlinear thing and find a linear approximation that's valid near a location? I can take the Taylor series, and I can take the Taylor series at these solutions Because those are convenient places to know what's going on in the neighborhood of. So the graphical description of are these stable or are these unstable is just a local Taylor series approximation of this fully nonlinear system. So we'll pick up from that next time. But the cool thing is when we do the Taylor series, it's not going to be any more complicated than this differential equation. It's going to be, we'll have a homogeneous part, which is the part proportional to temperature in these two terms. And we'll have an inhomogeneous part, which is the part, the 0th order part of the Taylor series. So if I Taylor series this, off we go. That's a system we know how to solve. That's all we're going to do. Okay?